Hello students, after studying this module, you shall be able to know about first differencing and fixed effect method for estimation. You shall also learn about the assumptions that are required while using either method. Identify the common assumptions in both methods and evaluate which method is better to use and in which conditions. Now I will give a brief introduction of the module. Panel data can be used to investigate the effect of unobserved factors that affect the dependent variable. Now this can be done in two ways. One, the unobserved effects, which means those are constant over time, and second, unobserved effects, those vary over time.
Now we will analyze differencing in two periods. Assuming I denotes the cross-sectional unit and T denotes the time periods, we can write the panel data model as YIT is equal to beta 0 plus delta 0 D2T plus beta 1 XIT plus alpha I plus UIT, where T takes the value 1 and 2. This is our equation 1. In this equation, YIT has I, which stands for individual, firm, state, city, etc., and T denotes the time period. In D2T, it is a dummy variable that equals 0 when T is equal to 1 and equals 1 when T is equal to 2. Note here, D2T does not change across I. Therefore, the intercept for time period T equal to 1 is beta 0 and intercept for T equal to 2 is beta 0 plus delta 0. Alpha I. It captures all unobserved time-independent factors that can affect dependent variable YIT. Generally, alpha I is called as an unobserved effect. It is also common in applied work to find alpha I referred to as a fixed effect that helps us to remember that alpha I is constant over time. The model 1 is called as fixed effect model or unobserved model or unobserved effect model since it captures unobserved effect alpha I. In applied work, alpha I is sometimes also called unobserved heterogeneity as well, or individual heterogeneity, or firm heterogeneity, or city heterogeneity, or state heterogeneity, etc. The error term used in this model, UIT, is often called idiosyncratic error or time-varying error. It is called so because it represents unobserved factors that change over time and affect dependent variable YIT. Now the question that arises is, how can we estimate the coefficients of this model given 2 years of panel data? One thing that can be done is pool the 2 years data and use OLS method, but this will require an assumption to be made. Pooled OLS will produce estimator of beta 1 if we assume that alpha I is uncorrelated with XIT. Model 1 can be in that case rewritten as YIT is equal to beta 0 plus delta 0 D2T plus beta 1 XIT plus VIT, where t is equal to 1 and 2. In this case, VIT is equal to alpha I plus UIT and is called composite error. And we must assume that VIT is uncorrelated with XIT in 2 periods case for OLS to produce consistent estimator of beta 1 and other parameters. This will hold true whether we use a single cross section or pool the 2 cross sections. Therefore, in case error term UIT is uncorrelated with XIT, then OLS will produce biased and inconsistent estimators if alpha I is correlated with XIT, and that will lead to a bias known as heterogeneity bias. But it is really just a bias that has caused from omitting a time independent or constant variable. Using model 1 for respective time periods, we can write yi2 is equal to beta 0 plus delta 0 plus beta 1 xi2 plus alpha I plus ui2 for time is equal to 2 in this case, and the equation is our second equation. Similarly, yi1 is equal to beta 0 plus beta 1 xi1 plus alpha I plus ui1 for time 1. This is our equation 3. Now subtracting 3 from 2, we get yi2 minus yi1 is equal to delta 0 plus beta 1 into xi2 minus xi1 plus ui2 minus ui1. This can be further written as delta yi is equal to delta 0 plus beta 1 delta xi plus delta ui. This is our equation 4, where this triangle is delta and denotes the change from t equal to 1 to t equal to 2. Please note the unobserved effect alpha I is not here in equation 4. It has been differenced away. Also, the intercept is actually the change in intercept from first year to second year. Equation 4 is called as first differenced equation, and OLS estimator of beta 1 is called first differenced estimator. First differenced equation is just a single cross-sectional equation, but each variable is differenced over time. Analysis of equation 4 requires certain assumptions to be made. For example, the first is that for each I, yit is equal to beta 1 into xit1 plus so on up to beta k xitk plus alpha I plus uit for t ranging from 1 to capital T, where the beta 1 or beta i's are the parameters to estimate and alpha I is the unobserved effect. The second assumption is that sample must be randomly drawn from cross sections. Our next assumption is that each explanatory variable changes over time, at least for some I, and there is no perfect linear relationship that exists among the explanatory variables. Our fourth assumption is that for each t, the expected value of idiosyncratic error given the explanatory variables in all time periods and the unobserved effect is 0. In other words, expected value of UIT given Xi and Ai is equal to 0. Our fifth or next assumption is that the variance of the difference errors unconditional on all independent or explanatory variables is constant. That is, variance of delta UIT given Xi is equal to sigma square for any value of small t equal to 2, 3 and so on up to capital T. This assumption ensures that the difference errors delta mu it are homostochastic. Our sixth assumption is that for all t not equal to s, the differences in the idiosyncratic errors are uncorrelated, which is conditional on all explanatory variables. It implies that covariance of delta UIT with delta UIS given Xi is equal to 0 when t is not equal to s. This assumption means that the difference errors are serially uncorrelated, which means that the UIT follows a random walk across time. Note, under assumption 1 to 6, first difference estimator of beta 1 is best linear unbiased estimator, obviously conditional on the explanatory variables. Our last assumption is that conditional on Xi, the delta UIT are independent and identically distributed normal distribution or normal random variables. After adding this assumption, first difference estimators become normally distributed and the T and F statistic from pooled OLS on the differences have exact T and F distributions. The most important of these assumptions is that delta UI is uncorrelated with delta Xi. This assumption will hold if the idiosyncratic error at each time t, that is UIT, is uncorrelated with the explanatory variables in both time periods. This assumption is also known as another version of strict exogeneity assumption made for time series models. Consider a problem of estimating the return to education with 2 years panel data on individuals. The model for the ith person is log Waze IT is equal to beta 0 plus delta 0 d2t plus beta 1 edu it plus alpha I plus uit, where t takes the values 1 and 2. This is our equation 5, where in this equation alpha I stands for unobserved ability, which is probably correlated with independent variable edu it. We allow different intercepts across time to account for aggregate productivity gains precisely and inflation if wage IT is in nominal terms. Since innate ability by definition does not change over time, panel data methods seem ideally suited to estimate the return to education. The equation 5 in first difference is delta log Waze I equal to delta 0 plus beta 1 delta edu I plus delta ui. which is our equation 6, and it can be estimated using OLS. The problem is that we are interested in working adults, and for most employed individuals, education does not change over time. If our sample has only a small fraction of delta edu I and different from 0, then it will be difficult to get a precise estimator of beta 1 from this last equation 6 unless we have a rather large sample size. Now we will look at differencing with more than 2 periods. We have just seen differencing using dummy variable when time period is just 2 years. Let us now move to the case when time period taken into consideration is more than 2 years. Suppose there are n individuals and t time period is equal to 3 years for each individual. A general fixed effect model in that case can be written as yit equal to delta 1 plus delta 2 d2t plus delta 3 d3t plus beta 1 x1it plus so on up to beta k xkit plus alpha I plus uit. This is our equation 7. For time period t is equal to 1, 2 and 3. Since there are n individuals and 3 time periods, so the total number of observations is 3n. Therefore, we have to insert 2 time period dummies in addition to the intercept by allowing a separate intercept for each time period because we have a small number of time period. Like we have done in case of 2 periods, the base period will be t equal to 1. The intercept for the time period t equal to 2 is delta 1 plus delta 2 and so on. If the unobserved effect alpha I is correlated with any of the explanatory variables, then using pooled OLS on the 3 years of the data results in biased and inconsistent estimators. The key assumption here is that the idiosyncratic errors are uncorrelated with the explanatory variable in each time period. In other words, covariance between xjit and uis is equal to 0 for all t, s and z. This is our equation 8. It means the explanatory variables are strictly exogenous after we take out the unobserved effect alpha I. This assumption, which is equation 8, rules out the case where future explanatory variables react to current changes in the idiosyncratic errors. If we omit an important time varying variable, then equation 8 is generally violated. Measurement error in one or more explanatory variables can cause this equation to be false. If alpha I is correlated with xjit, then xjit will be correlated with the composite error vit, which is equal to alpha I plus uit under equation 8. In this case, we can eliminate alpha I by differencing adjacent periods. In case when t is equal to 3, we subtract time period 1 from time period 2 and time period 2 from time period 3. We get delta yit is equal to delta 2 delta d2t plus delta 3 into delta d3t plus beta 1 into delta x1it plus so on up to beta k into delta xkit plus delta uit. This is our equation 9 for time period 2 and 3. Note that we do not have a difference equation for t equal to 1 because there is nothing to subtract from equation for t equal to 1. Equation 9 represents two time periods for each individual in the sample. If this equation satisfies the classical linear regression model assumptions, then pooled OLS will give unbiased estimators, and the usual T and F statistics are valid for hypothesis. Note that this equation 9 does not contain an intercept, which is inconvenient for computation of R squared. Equation 9 contains the differences in the ear dummies D2T and D3T, while estimation for T equal to 2, delta D2T is equal to 1 and delta D3T equal to 0. Similarly, for T equal to 3, delta D2T is equal to minus 1 and delta D3T is equal to 1. When time intercepts are not of direct interest, the model can be estimated using first difference equation with an intercept and a single time period dummy. Usually for third period, the model will be like this, where we have delta YIT equal to alpha 0 plus alpha 3 D3T plus beta 1 delta X1IT plus so on up to beta K into delta KIT plus delta UIT for T equal to 2 and 3. This is our equation 10. Similar exercise can be done for the case when time period is more than 3. Now we will look at demerits of using first differencing in panel data. In this module, we have used first differencing method in panel data to eliminate a time constant unobserved effect. It is a valuable method for obtaining causal effect, but there are certain difficulties associated with it. The first difficulty is when key explanatory variables do not vary much, the first difference method leads to potential problems in estimation. Moreover, when we do have sufficient time variation in the XJIT, first difference estimation still can subject to serious biases. Assumption of the strict exogeneity is considered as crucial assumption in this method. But having more time periods generally does not reduce inconsistency in the first difference estimator when the regressors are not strictly exogenous. For example, if yi t minus 1 is included among the xj it. The second problem is that the first difference estimator can be worse than pooled OLS if one or more explanatory variables are subject to measurement error. Differencing a poorly measured regressor reduces its variation relative to its correlation with the differenced error caused by classical measurement error. That would lead to potential sizable biases. In the subsequent section, we will discuss about fixed effects estimation. There exist several ways to eliminate the fixed effect alpha I. An alternate method which is considered better under certain assumptions is called fixed effects method. Consider a model with single explanatory variable. For each I, we can write YIT is equal to beta 1 XIT plus alpha I plus mu IT, where T is equal to 1 to capital T. This could be written as our 11th equation. Averaging the above equation for each I, we get yi bar is equal to beta 1 into xi bar plus alpha I plus ui bar. This is our equation 12th, where yi bar is equal to T inverse into sigma yit, and T ranges from 1 to capital T and so on. Because alpha I is fixed over time, it appears in both 11 and 12 equations. Subtracting equation 12 from equation 11 for each t, we get yit minus yi bar is equal to beta 1 into xit minus xi bar plus mu it minus ui bar, and t takes the values from 1 to capital T. Or y double dot it is equal to beta 1 x double dot it plus u double dot it, where t takes the values from 1 to capital T, and this could be written as equation 13. Now in this equation, yit double dot is equal to yit minus yi bar and is time demean data on y, and similarly for xit double dot and uit double dot. The fixed effect transformation is also called within transformation. Note that the unobserved effect, that is alpha I, is not there in the equation 13, which suggests that this equation should be estimated by pooled OLS that will be based on time demeaned variables. The estimators that we get from this is known as fixed effect estimator or within estimator. If we add more explanatory variables to the equation, it causes few changes. Let the model be defined as yit is equal to beta 1 into x1it plus beta 2 into x2it, so on up to beta k xkit plus alpha I plus uit, where t takes the values 1, 2 up to capital T. This is our equation 14. Here we simply estimate the model by pooled OLS regression using time demeaned on each explanatory variable. The time demeaned equation for each cross-section unit is y double dot it is equal to beta 1 x double dot 1 it plus beta 2 x2 double dot it, so on up to beta k xk double dot it plus u double dot it, where t takes the values from 1 to capital T. This is our equation 15. Under a strict exogeneity assumption on the explanatory variables, the fixed effects estimator is unbiased. The idiosyncratic error uit should be roughly uncorrelated with each explanatory variable across all time periods. The fixed effects estimator allows for arbitrary correlation between alpha I and the explanatory variables in any time period, like in first differencing. Now, because of this, all time invariant explanatory variables for I get eliminated. Now, following are the assumptions that are needed for estimation using fixed effect model. First, for each I, the model is yit is equal to beta 1 into x1it plus so on up to beta k xkit plus alpha I plus UIT, and T varies from 1 to capital T. In this, beta j's are the parameters to estimate, and alpha I is the unobserved effect. The second assumption is that sample is drawn randomly from cross section. The third assumption is that each explanatory variable changes over time for at least some I, and there is no perfect linear relationship that exists among explanatory variables. Fourth assumption is that for each time period t, the expected value of the idiosyncratic error given the independent variables in all time period and the unobserved effect is 0. That means expected value of UIT given xi and alpha I is equal to 0. Assumption 4 is the key assumption, stating strict exogeneity. All the above assumptions lead to consistent estimator with a fixed t as n tends to be infinity. The fifth assumption is that variance of UIT given xi and alpha I is equal to variance of UIT and is equal to sigma u square for all t, which is t equal to 1 to capital T. The sixth assumption is that for all t not equal to s, the idiosyncratic errors are uncorrelated, which means conditional on all explanatory variables and alpha I. Now this can be expressed as covariance of UIT and UIS given xi and alpha I is equal to 0. The last assumption, the seventh, is that conditional on xi and alpha I, the UIT are independently and identically distributed IID as normal with mean 0 and variance sigma u square. Note, fixed effects methods apply immediately to unbalanced panels, but we must assume that the reasons some time periods are missing are not systematically related to the idiosyncratic errors. Let us now discuss the topic of degrees of freedom in brief. When we estimate equation 15, that is time demeaned equation, using pooled OLS, we have n, capital N into capital T total observations and k independent variables. Note that there is no intercept term in equation 15. It is eliminated by fixed effect transformation. Therefore, we have n into t minus k degrees of freedom, which is incorrect. For each cross-sectional observation I, we lose 1 degree of freedom because of the time demeaning procedure. In other words, for each cross-section I, the demeaned errors u double dot it add up to 0 when summed across t. So we lose 1 degree of freedom. Therefore, the appropriate degrees of freedom is equal to n into t minus n minus k, and this is equal to n into capital T minus 1 minus k.
Now we will discuss fixed effects or first differencing. Apart from pooled OLS, we have studied two other methods for estimating unobserved effects models, namely first differencing, also denoted as FD, and fixed effects. Now the question arises that which one should be used. The answer is when t is equal to 2 or 2 time periods, the first differencing, the fixed effects and all test statistics are identical. So it does not matter whichever we use. The equivalence between both these methods obviously requires that we estimate the same model in each case. As discussed earlier, we include an intercept in FD equation, which is actually for the second time period in 2 time periods model. Fixed effects estimation must include a dummy variable for second time period in order to be identical to the FD estimates that include an intercept. With the time period is only 2 years, FD can be straightforward used in any econometrics and statistical package. It also makes computation of heteroscedasticity robust statistics easy because in 2 time periods, FD estimation is a cross-sectional regression. When time period is greater than or equal to 3, FD and fixed effects estimators are not same. Both are unbiased and consistent under the assumptions which we have numbered 1 to 4 earlier, so we cannot use unbiasedness as a criterion. For large N and small t, the choice between FD and fixed effects hinges on the relative efficiency of the estimators, and this is determined by the serial correlation in the idiosyncratic errors UIT. So when UIT is serially uncorrelated, fixed effects is more efficient than its counterpart. Moreover, standard errors reported from fixed effects are valid. Since unobserved effects model is typically stated with serially uncorrelated μit or UIT, the fixed effects estimator is used. But in applied works, it can be expected that the unobserved factors that are time variant may be serially correlated. If UIT follows a random walk, then the difference delta UIT is serially uncorrelated. So, I have said first differencing is better method for estimation in such a situation. However, when t is large and especially when n is not very large, say for example n is 20 and t is 30, we must exercise caution in using fixed effects estimator in such a situation. Although exact distributional results hold for any n and t under the classical fixed effect assumptions, inference can be very sensitive to violations of the assumptions when n is small and t is large. First differencing has the advantage of turning an integrated time series process into a weakly dependent process. Therefore, if we apply first differencing, we can appeal to the central limit theorem even in cases where t is larger than n. Let's summarize the discussion which we have done so far. We have learned in this module that panel data sets are more useful when controlling for time constant unobserved features of people, firms, cities, etc., which are individuals mainly. Now, one way to remove the unobserved effect is to difference the data in adjacent time periods, and standard OLS analysis can be used on the differences in such a situation. We have also learned that the usual inference procedures are asymptotically valid under homoscedasticity, and exact inference is available under normality assumption. For more than 2 periods, we use pooled OLS on the difference data. In that case, we lose the first time period because of differencing. In addition to homoscedasticity, we must assume that the differenced errors are serially uncorrelated in order to apply the usual T and F statistics. We have also learned and have understood two common methods for estimating panel data models with unobserved effects. I am sure you can recall we have said that fixed effects estimator is efficient when UIT are serially uncorrelated and homoscedastic, and we make no assumptions about correlation between the unobserved effect alpha I and the explanatory variables.